This video is about implicit differentiation, and it will tell you how to differentiate y in terms of x even if you do not have an explicit formula. That sounds kind of magic, right? So let's get started. What we usually have is a formula for y in terms of x. In this case, we say that y is expressed explicitly because it's an explicit formula in terms of x. But that is not always the case. For example, if you start with an equation which is x squared plus y squared is equal to 4. In that case, we don't have an explicit expression for y in terms of x, which is why we said that this equation because of the equal, is an implicit equation, and implicit because we don't have an explicit formula. Now we recognize this equation, we've seen it before. It's the equation of a circle of radius 2 centered at the origin. It's there. The explicit formula for y in terms of x wasn't given to us, but maybe we can just find it. And we very soon run into a problem. If you pick a value for x, there is not one value for y which corresponds to this x. There are two. That means we will never get a formula in terms y equal to f of x that describes the whole curve. We say that this curve doesn't pass the vertical line test. If there are some places where you could get 2 points of intersection between a vertical line and your curve, you know that you will not be able to write your curve as the graph of a function. And in that case, we're not sure what to do. Say we're interested in finding the slope of the tangent line, because clearly we can draw a tangent line. This tangent line must have a slope. The way we found it so far was to find this derivative. But how can we do that if we don't have a formula for y in terms of x? There is something we could try. Since it's not possible to represent the whole curve with one function, we could represent the whole curve with several functions. So what we could do is split the curve into several pieces such that each piece is the graph of a function. Now this part passes the vertical line test. If I draw a vertical line, it's going to cut my curve in only one point. And that means I can write y in terms of x. So let's try to see what these functions would be. The equation of our curve is x squared plus y squared is equal to 4. If I want to solve for y, I'm going to subtract x squared from both sides, and I get y is equal to plus or minus 4 minus x squared. So that gives me one solution where y is greater than or equal to 0, and one solution where y is less than or equal to 0. A positive y means we're above the x-axis, and we get this graph and this function. And negative y means we're below the x-axis, and we get this graph and that function. So now we can actually find the derivative we were after, and we're going to do it for each of these two functions. Let's start with the function y is equal to square root of 4 minus x squared. dy dx, that's the derivative of a square root. We recognize the chain rule, so it's 1 on 2 times the square root. Keep the inside function unchanged and multiply by the derivative of the inside function. Now the question says try to write that in terms of x and y. So my y is this, and I recognize my y here, so that's my y. I can also see that the 2's cancel. So in the end, I'm left with minus x on y. Let's do the same for the other one. So this time y is different. There is a negative sign in front of it compared to the first one. Still the chain rule. Minus 1 on 2 times square root of 4 minus x squared times the derivative of the inside function. And I get this minus 2x. If this is too fast for you, you can write the details of the chain rule. Now the 2's cancel, and what I recognize here, that's my y. So what I get in the end, I get this minus x from here and the y at the bottom. So I guess minus x on y. And notice that something interesting happened. We have different formulas, but in both cases, we get the same expression for the derivative expressed in terms of x and y. It would have been great to get those two at once, right? Especially since we think sometimes we're going to need to split the curve into 2, 3, 4, 5 functions. I have some good news for you. The good news is it's possible to compute the derivative of y in terms of x without having an explicit formula for y in terms of x. I really hope you're impressed. That's crazy. So that means you don't have to worry about how many pieces you would split your curve. You just get one derivative that works for all of them. Let's see how we're going to do that. Let's start with the example. So we assume that y is a function of x, although we don't have an expression for the function. Now, if you look at the example, these two expressions are equal. Well, if they're equal, their derivatives will be equal. So what we do is take the derivative with respect to x of both sides. The derivative of the left-hand side will be 2 times the derivative of y with respect to x. That's a dy dx. Then the derivative of y squared, so that's a function inside a function, because y is a function of x inside the square function. So we get 2y times the derivative of the inside function, which is dy dx. Now we're taking the derivative with respect to x, so the derivative of x cubed is 3x squared. And the derivative of 4x with respect to x is 4. That's the derivative of the left-hand side. On the right-hand side, we have a constant, so the derivative is 0. At that point, try to remember what you're trying to find. You're trying to find dy dx, so your unknown is this dy dx. So don't panic. This just looks like an equation which would be like 2 times what I'm looking for plus 3 times what I'm looking for plus something is equal to something. What you would do in that case, I'm sure, is to combine those two by factorizing capital X, and you would subtract 10 from both sides to put all the terms that don't contain the thing you're looking for on the right-hand side. We do the exact same thing. We factorize this thing we're looking for, which is dy dx. Coming from this first term, we get a 2. And coming from this second term, we get a 2y. So if you'd like, what we've done is combine those two. Now we said we would add to both sides whatever is needed to move this term to the other side. And so we are getting equal to 3x squared minus 4. Right, so it's the same in this equation. We get to 5x is equal to 2. If this is what you want to find, so what we want to find is dy dx, in this simple case, you would be dividing by the coefficient of the thing you're trying to find. So we're going to be dividing by the coefficient of the thing we're trying to find. So we divide both sides by 2 plus 2y. And we get dy dx is equal to 3x squared minus 4 over 2 plus 2y. So, as promised, we've been able to find the derivative of y in terms of x without ever finding the formula that gives y in terms of x, or the formulas, because they could be several. So this was just an example, and we'll see that it just follows a very general pattern. So a little bit of vocabulary first. When you have an expression with two variables like that, a function of x and y is equal to 0, that forms an implicit equation. If what you want is dy dx, what you will do, exactly what we did below, you differentiate both sides of the equation with respect to x, using the chain rule wherever there is a y, because your y is a function of x. And then you rearrange to make dy dx the subject, which is what we did starting from here. And we got a formula for the derivative in terms of x and y. Remember our first example with the circle? where we split the curve into the graph of two functions and differentiated them separately. Well, let's try to use a new technique and just convince ourselves that this is so much better. So we start from our implicit equation, which is this, and we differentiate both sides. So I'm starting from that, and I differentiate both sides. Derivative with respect to x. I'm going to get 2x, and applying the chain rule to y squared, the derivative of y squared with respect to y is going to be 2y, and then I multiply by dy dx. That's the derivative of the left-hand side. I also take the derivative of the right-hand side, and the derivative of 4 is 0. This example is easier than the previous one, because our unknown is in only one place. So we will get 2y dy dx is minus 2x. That means dy dx is negative 2x on 2y. We can cancel the 2's. And of course, we get the same expression we got earlier, but that's just been easier. Since this was a little bit abstract, let's see that it actually matches our intuition and really corresponds to the slope of the tangent line. So question alpha, let's look at what happens at the point 0, 2, which is this one. So we know that the derivative of y with respect to x is always minus x on y, and if we sub in our values, x is 0 and y is 2, and we get 0. That means that the slope of the tangent line is 0. That's a horizontal tangent line. That's exactly what we're getting. Next, we move on to the point square root of 2, square root of 2. So it's this one here. So we're looking, so I'm calling this beta, so we're expecting a negative value. And indeed, our minus x on y will be minus square root of 2 on square root of 2, and it will be negative 1, which is consistent with the drawing. The next one is negative square root of 3 and 1. It's there, so that corresponds to gamma. So this time we expect a positive value because the slope of the tangent line is positive, and something probably greater than 1. Let's see. So our formula is always the same, and we just sub in the values we have for x and y. And we get plus square root of 3, which is positive and greater than 1 as expected. The last one is interesting too. So we are now looking at the point with coordinates 2, 0, which is there. So we're looking at this tangent. So this is my case delta, and formula is always the same, and then something happens. If I want to sub in the values, I would need to sub in y equal to 0. So I would be dividing by 0, so I get something which is undefined. And that's not surprising because vertical lines don't have a slope. Their slope is undefined. It would need to be infinity if you wanted to pick a value, but infinity is not a number. So we say it's undefined. So again, we get that what we get is consistent with the drawing. Let's now see on an example how implicit differentiation can be used to find the equation of a tangent line. The steps to find the equation of a tangent line are always the same. Step 1, you find the slope of the tangent line using the derivative at your point of interest. Step 2, use the point slope form of the equation of a line to find the equation of the tangent line. You got the slope, the gradient from step 1, and the point of interest is given in the question. I wrote in green the steps which are common to all the questions where you need to find the equation of a tangent line, and now I will write in blue the steps that are specific to this example. The equation of the tangent line is dy dx, and what's specific to this exercise is the point I want. So I want this at this point. So I need to find dy dx. Since what I get initially is an implicit equation, I will need to use implicit differentiation. That means I'm going to differentiate both sides of this equation with respect to x. The derivative of y cubed with respect to x is 3y squared dy dx. If you're not sure why, let me do this on the side for you. What you want to differentiate is z is equal to y cubed, and you want to differentiate it with respect to x. So using the chain rule that tells you that dz, that's dz dy times dy dx. The derivative of y cubed with respect to y is 3y squared, and then you have this dy dx, and it's the same for all this term. So I just take this and put it there. The next term will be differentiated using the product rule. So I have this 3, that's a constant times a product. So I'm gonna get u dash, so u is x, u dash v, easy, plus u, so 3x, v dash dy dx. Next term, 3x squared. That's the derivative of the left-hand side with respect to x. Now the derivative of the right-hand side with respect to x will be the derivative of 0, that's 0. At this point, it's important to remember what we're trying to do. We are trying to find dy dx. So what we will do is put on one side all the term with dy dx and factor out dy dx. So since here we have dy dx times 3y squared, in this parenthesis we'll get a 3y squared. Similarly, if we look at this term, we get dy dx times 3x, so in this bracket we get a plus 3x. Now we are left with those terms, these two terms, which don't have a dy dx in them. So what we're going to do is subtract them from both sides. So if I subtract 3y's and 3x squared from both sides, I get this. Now what I want is dy dx, and I have dy dx times something, so to get just dy dx I will divide by the something. So I'm going to divide both sides by 3y squared plus 3x. So I'm going to get dy dx is equal to minus 3y minus 3x squared over 3y squared plus 3x. We can divide the top and the bottom by 3. So we get minus y minus x squared over y squared plus x. This formula gives the derivative at each and every point on this curve. Now we're not interested in all the points, we only want this one. The one with coordinates negative 3 halves, negative 3 halves. So we just sub this in. So we get minus 3 halves minus 9 on 4 over 9 on 4 plus 3 half. And if you look, you notice that the top and the bottom are just opposite, which means that when you divide, you will get negative 1. So step 1 completed, we found the slope. Done. We move on to step 2, where we use the point slope formula equation of the line and we just sub in the values we have. Y minus the y coordinate of my point, so minus 3 half is equal to the slope, that's negative 1, times x minus x1, so I get x1 from there. And if I simplify this, I'm going to get y plus 3 halves is equal to minus x minus 3 halves, and by adding minus 3 halves to both sides, I get minus x minus 3. If you'd like to get a little bit more practice, this is a very similar problem, and as you can see, the answer is given at the bottom. Thank you for watching this video on implicit differentiation. We learned to find the derivative of y with respect to x, even though we do not have an explicit formula for y in terms of x. The only thing we had to start from was an implicit equation. And then we saw how to use this on an example to find the tangent line to a curve.